content today, which is the part of the online Pratidhwani series, and which the department is organizing. The webinar series is sponsored by Author Cafe. Author Cafe is an online platform that aids with writing, collecting, organizing, collaborating, and publishing your research content through features and integrations with products like Mendeley, Zotero, Orchid, Prof, and so on. Think of it like Google Docs, specially designed and developed for the academic community, and much more. Okay, so we are thrilled to have Professor Satish Pandey from the National Museum Institute, New Delhi today. Before we start, a couple of technical details. Please do not unmute yourself during the talk. If you have any questions, please type them in the chat box, and we will try to get at least some of them to the speaker after the talk. I would like to request Professor Ramanan from the Department of Chemistry, IIT Delhi, to introduce the speaker. Over to you, Professor.
Thank you, Prof. Samik, and it's really a pleasure to have Dr. Satish Pandey from the National Institute of Museum. He is also currently the head of the department, and he has been working for the last few years over there. He had his graduation from both masters as well as doctoral degree from the University of Oxford. And it is very interesting that he chose a topic, which is basically he's a chemist, and then he chose a topic in heritage sciences. So he has been very keen because India has several, monuments all around, and Delhi has several of them, and there are quite a few around Delhi also. You don't need to go around the country, but even in and around Delhi, there are quite a few of them. So his interest is basically to look at, how to conserve many of these monuments. Maybe it's stones, maybe there are various, metal objects or other materials that undergo decay because of n number of reasons, right? Environmental and various other things. So his interest is basically to get an insight into the mechanism, how that happens, and how to preserve them. And he's doing an excellent job, especially, the in and around Agra, mainly the, the marble stones. See, this is one of his areas where he has worked considerably. And it is really, a pleasure for us to have him here, because I have been trying to get him for the last 2 years since I started interacting. And one reason or the other, somehow it didn't happen. But finally, Satish is here to share his experiences of, interacting with the various monuments and other things, And Satish, now we are looking forward to listen to you.
Thank you, Ramanan. Thank you, Shamik. And I'm really very sorry that I've taken a couple of years to come and speak to you. I should have done it earlier, and I should have done it more frequently than just once. Although, as Ramanan has introduced me, that my area of research is basically into stone monuments, their deterioration and conservation. But today I'm going to talk about how world has used science in cultural heritage. So it's kind of a very basic presentation where I'm going to talk about how different scientific tools and techniques have been used to answer questions arising in cultural heritage, how we study and interpret cultural heritage, art and cultural heritage using science. So the discipline is not new. It has been in practice for more than a century. However, in India, it's still, taking its shape. So talking about science in art and cultural heritage, there are different, as you would have read in my abstract that I shared, there are different terms and terminologies people use to define the application of science in cultural heritage. And if I have to name some of them, you would see that I'm sure you must have heard these terminologies before: archaeometry or archaeological science, conservation science, and technical art history. So art history, which is technical, is quite intriguing subject. So when I started my career, this was very kind of subject close to my heart. So in terms of archaeometry is one of the oldest discipline where we use science in art and cultural heritage. Conservation science and technical art history are relatively newer. Archaeometry started somewhat in 19th century, and once the scope of archaeometry started increasing, people thought that archaeometry is not an appropriate term. We should call something a little bigger, where it can encompass more of newer scientific disciplines, and therefore it was called archaeological science. So today we use these two terms, in conjunction. People call archaeological science, people call archaeometry, and both are the same thing. In fact, technical art history and conservation science are also similar, quite similar. The differences are just in what we are trying to gain out of it. What is the motivation of doing those scientific research? So looking at archaeometry, if I have to talk about archaeometry first, a number of things that one can use science in. First of all is artifacts provenance, looking at the source of material, source of the artifact, where it has come. Then the technology, how it was produced, what kind of technique the ancient civilizations used to produce a particular work of art. I'm fairly sure that all of you would know dating and chronology systems. Radiocarbon dating is one famous dating system, but that's not the only one. There are about a dozen dating systems that exist, and all have their own advantages and disadvantages. And finally, biomolecular archaeology. I'm going to talk about the first three, how science is applied into provencing, studying technology and dating and chronology a little bit. But I'm skipping biomolecular archaeology because this is something altogether different from what I'm going to talk about. It goes more into ancient DNA and all those kind of things. So we will skip biomolecular archaeology for today. We may have chances to speak about it sometime later. Now, talking about provenance, if I show you a couple of data here, provenance is trying to understand where was the raw material sourced, how the objects arrive in that society or culture, and there can be multiple ways. One, that ancient societies procured raw material from a different source, produced the artifact locally. The other is trade and commerce, by which the material from other civilizations could have traveled to a particular civilization or society. Now, there are different ways of studying provenance. One is based on trace element analysis. So studying the tracer element in excuse me. In terms of understanding provenance of a material, the larger groups of material in a, say for example, if it is a copper vessel, copper particularly, it would be the major element. So all major element, it is possible that they were added deliberately. So, in making bronze, the tin was added, making brass, the zinc was added, and these are all deliberate additions. But trace element in the ancient societies were not deliberate additions. They were there by virtue of their presence in the ore. And therefore, if you look at the trace element and their signatures, it is quite possible to trace the origin of the artifact that you're investigating today. Now, if you look at the first image here, can you see my mouse cursor?
Yes, I can see it. Yeah, okay. We can see.
Right. So you can clearly see that there are three different groups of artifacts. These are potteries which were studied using samarium and lanthanum trace elements in the pottery, and you can see that there are three distinct groups forming, which indicate that these three types of pottery came from three different sources of ore or the soil. Now here in this one, this is the plotting of obsidian wares in one of the societies, Mayan society in fact. And you can see again the grouping is based on manganese, as compared to sodium, and manganese would be a trace element. And looking at the comparison, you can see that all these obsidian material came from different locations, and they group differently. And it is not just one analysis. You see multiple samples taken, and they group very distinctly from each other. And therefore, this gives you an idea of the source of raw material, or the source of the object itself, where it came from. Now, the second provenancing can be based on, which is much more precise, because trace elements sometimes ditch you. So isotope analysis, particularly stable isotope analysis, is something that is much more precise in provenancing. And here, if you see, two different data produced here, and the red sample dots were Athenian silver coins, and the square dots are Laurian ores. And the kind of fit they have indicates that all these Athenian silver coins were made from the ore recovered from this site, this quarry. In another study, if you see, this is about late Bronze Age metals. There were two sources of ores. One was this, which is, this is a kind of comparison between these two metals. And if you see this one, this is the Mitterberg ore, which is concentrating right here. And then it has Schwarzbixleg ore, which is concentrating right at the top. So these are two ore analyses. In between, if you look at these were, the triangles, black triangles that you see were late Bronze Age ingots. And ingots were normally, these ingots are stock metal that were, after smelting of the ore, the pure material is collected, solidified, cut into stackable pieces, and then stored. And those pieces were later used to create artifacts or objects, whatever the civilizations wanted. Now, if you look at, so these are in fact pure iron metal. So here, if you see, half of these, or maybe larger amount of these, came from these ores here, from Schwarzbixleg or Fallor ores. But they also have been produced from the Mitterberg ores. So they're scattered all over the place. Now, if you look at the metal signature, most of the metal signature lies right in between. What it indicates that the ingots that were produced from both these sources were mixed. It was not segregated, they were mixed, and then the metal was casted, and therefore the metal signature lie right in the center. And that indicates mixing of these two types of metals. This also suggests that this kind of analysis becomes very tricky when metals are being recycled. So this also suggests that it may be possible that the ores, the ingots here, they may have been produced into a metal, and then those metals were recycled, mixed with these metals, and then prepared again. So the object that the scientists were analyzing could have been the result of a mixing of, or recycling of those. So the scientific investigation here. Now, I have a box here which is interfering how it should. Okay, gone. Now, so that was provenancing. In terms of technology, we also need to study and see what was the technology that was used in production of an artifact, and what could be better than talking about iron pillar. I'm sure all of you must have seen iron pillar here in Delhi. It's not the only one. There is one in Dhar, which was longer than this, now broken into 3 different pieces and lying in Dhar. Professor R. Balasubramaniam from IIT Kanpur investigated the rust-proof nature of these iron pillars, and he concluded that if you see in this microstructure here, you see a kind of dark amorphous layer right in the inner side, and this is the rust that forms on the surface. In another, so this is Dhar pillar. This is the Delhi iron pillar, and he is shown that, if you see right in the middle here, there are 3 distinct layers, and the middle layers are kind of amorphous in nature and dark in color. What he found, that this amorphous layer is basically iron hydrogen phosphate, which is formed right on the metal surface, and therefore the corrosion which is happening on the surface doesn't penetrate inside the metal. This is a very thin film, so you won't even notice. And presence of phosphate, phosphorus, is what making Delhi's iron pillar rust proof. So this is the gift of science to understanding ancient technology. This is one example. There are many, there are hundreds. Now, this is a very recent study published, and Brahman has shared this study with me quite some time ago. These are 6th century BC potteries from Tamil Nadu, which were investigated, and they were, the black coating inside the vessels were fired in such a way that they formed nanotubes inside, and thus making it a very, very strong material. Now, it is not necessary that in 6th century BC they knew the science of nanotechnology. They certainly didn't. But what they knew, how to make their vessels harder, durable, and because it was coated on the inner side, the idea was that whatever food preparation you're making, the material from the pot itself at higher temperatures is not mixing with your food. So a durable coating. So this is what it resulted, a very durable, very hard coating. Because of the firing technology they had, there was development of nanotubes in the pottery layer. Now, in terms of dating and chronology, I'm sure you all have heard about radiocarbon dating. Radiocarbon dating is one very widely applied technique, and this is the radiocarbon dates of some of my samples where we did excavation in Haryana, in Kunal 2 years ago. And some of the charcoal samples were sent to Beta Lab in Florida, in Miami, for radiocarbon dating. And you see, this is the confidence date, about 95%. Let me see the confidence level. 76% of confidence level, and the dates are about 2800 BC. The calibrated dates are about 2800 BC of those charcoal samples which we sent. So that indicates that that was an Indus Valley civilization, an Harappan civilization. So these dates coincide with, they corroborate what Indus Valley civilization is, and so we call it roughly 3000 BC. This was not going up to 3000 BC, but 2800 is also a very, very significant date. So radiocarbon dating is one, but there are a number of other dating techniques. You have dendrochronology, you have radioactive isotope-based dating systems, you have thermoluminescence dating. I'm not going to discuss all of them, but then all of them are scientific disciplines which are widely used in archaeology. In terms of biomolecular archaeology, why I'm not trying to discuss this here, because this is altogether different science. In biomolecular archaeology, people do residue analysis. If you have an archaeological pot recovered from an archaeological expedition, scientists can try and look into if there is any residue of food products left survived in the pores of the pottery. And that can lead to reconstruction of a lot of things, including what was the purpose of the vessel, what was the uses of the vessel. Number of scientific analysis studies have found milk, residue of milk in the pottery or meat in the pottery, and things like that. But it depends on what kind of climatic condition the pot is preserved in, because most of the time organic matters don't survive for a very long period. The biomolecular archaeology is basically a DNA science of studying ancient DNAs, and people have done all sort of studies, in fact, trying to look into kinship and relationship of the burial skeletons. ancient diets, what kind of diet people used to eat, origin and spread of agriculture, how agriculture developed into a particular society, diseases in the past civilizations, or death because of a particular disease. Everything is possible to be deciphered by using techniques of biomolecular archaeology. So we'll skip it for now. Now, this is technical art history. Technical art history developed out of a necessity. So art history as a discipline has conventionally been perceived as a study of works of art in their historical and stylistic context. For example, genre, design, format, style, and all those kind of things. Connoisseurship has been widely used method for trying to understand art, trying to attribute it to people for a very long time, centuries. However, the idea of connoisseurship is loaded with many controversial connotations. In art history, the ability to attribute which artist painted a particular painting, or when they painted and how they painted, is basically a very difficult thing to be attributed by just looking at the painting. Now, the practice of art connoisseurship is the cognitive process, which is just, it comes from how trained your eyes are, how trained somebody is in looking at the artwork. And it comes with experience that you constantly looking at the artwork of a particular artist. For a very long time, you've been sourcing, trying to look into the style and technique of the artwork of that particular artist, and you develop an understanding about the artwork. But then there are chances of error, that you may make a mistake. They can be fake, they can be copy, and I'll cite some examples right there. So a very famous German art historian, Max Friedlander, pointed that judgment.
Just to interrupt you, we are not able to see the slide. This is a.
I don't know why.
And see your mouse. Yeah, now it's okay.
Okay, what was the issue?
I have no idea. Now it has come back. Yeah.
Right. Okay. So, so this was a well-trained eye. It can be well-trained. It can't have for 100% certainty. It can say that the artwork or technique or style belongs to this particular artist or that particular artist. Now, a very famous art historian. I'm just not getting his name. Anyway, I'll probably find out. Yes, Ernst Gombrich, and he compared the field of art history, and it was a sarcastic remark, a satire, and he said that the art history, the field of art history is much like Caesar's Gaul, and because the Gaul was divided into 3 different parts inhabited by tribes, he said that the art history is also like a Caesar's Gaul, divided into 3 parts, inhabited by 3 different, though not necessarily hostile tribes: the connoisseurs, the critic, and the academic art historians. But today, the discipline, I would say, that is also inhabited by a few more modern tribes, and that includes conservators and conservation scientists. So art history has become technical art history these days. Not that it has replaced art history, but it is an addition to the knowledge that we had from art history. So art history includes study of artist material, their technique and style, intention and authenticity and attribution. So looking at artist material, what kind of material a particular artist used, what techniques he or she followed, whether the artwork that was created by an artist centuries ago were modified, forged, altered, changed, and whether it is still possible to attribute the artwork to a particular artist is what we look at with the help of science. So when we look at artist material. This is, an Egyptian coffin fragment with Egyptian blue pigments in it. Now, can you notice blue anywhere? I don't. So if you see the yellow arrows here, they point onto black pigment, but the red ones point onto blue pigment, which has altered over a period of time and converted it into black. There can be multiple ways of this type of conversion. Egyptian blue is Egyptian blue is one of the first synthetic pigments that were created about 3000 BC. And this is a double salt of calcium and copper silicate. Now, what happens, why this darkens? There are a number of theories, but one is that the copper breaks out of the pigment, converts into copper oxide, which is black in color. So this one, the blue pigment converting into a black pigment, were studied using multispectral imaging. Multispectral imaging, as the name suggests, you have multiple wavelengths of spectrum, trying to study the painting under those and convert the resultant image into a false color for better understanding and visualization. So now this is the fragment here. You can see the original fragment, and this is visible induced infrared luminescence. Since it is infrared luminescence, you see this all black and white, and this is white fluorescence that is coming, and you see none of those black pigments are fluorescing. Only blue pigment, which is the Egyptian blue has property to fluoresce in visible induced infrared luminescence, and therefore all the blue pigments appear in IR luminescence, induced IR luminescence. Now, if you convert into false color, all the red areas are where blue was used originally. So this is how one can study artist material. This is one instance of science that, you think of a scientific technique and will find uses in art and cultural heritage. You innovate a scientific technique and will find uses in art and cultural heritage. So this is another technical study about understanding pigments, and this is from India, although written by British scientists. This is Bundi Palace, and wall paintings of Bundi Palace, very explicitly, beautifully decorated painting. And these yellow pigments that you see here are Indian yellow. I'm not sure if you know about Indian yellow. Indian yellow was a pigment that was banned early 19th century because this was produced from cow's urine. The cows were fed on mango leaf, and because they were fed on mango leaves, the cow would have jaundice. The urine become yellower, and then the urine is collected and dried to make these pigments. Very laborious, very tedious process, but at the end of it, the cow would die, and therefore it was banned. Now, looking at these pigments, not only in India, these pigments were exported across the globe, and a lot of Western work of art you will find with uses of Indian yellow. Now, this is luminescence again, and this is a luminescence of UV radiation, and luminescence is in the visible range. So it was illuminated with a UV radiation between 280 and 370 nanometers. And the luminescence, which comes in a visible range, gives you bright yellow luminescence of Indian yellow. But in the IR range, they still fluoresce. They also give a bright fluorescence in the IR luminescence. It's a very peculiar property of Indian yellow. So this is another technique how you can study pigment. All these pigments can also be studied by all these destructive techniques like scanning electron microscopy or Raman or FTIR. But most of the time when we're working on cultural heritage, we do not have liberty to take samples. And therefore, our analysis has to develop techniques that can become non-invasive, non-destructive, so that they work without the idea of taking samples. And this is one of them. There were samples collected, of course, from these wall paintings, and these were studied with HPLC time of flight analysis. And you can see, this was a reference sample, and this is the wall painting sample, and you can see it is showing, euganthic acid and euxanthone sulfonate. These are the components of Indian yellow, and it's perfect match showing that this is Indian yellow. Right? So this is another way of studying artist material. There are hundreds of ways of studying artist material, some destructive, some non-destructive, non-invasive. So we try and use non-invasive. Technique and style. I talked about technique and style. When we say technique and style, what is beneath the paint layer, we cannot see, but we try and see to understand how the painting was conserved, or how the painting was painted. Now, this is the painting of King Edward VI, and this is in collection of National Portrait Gallery in London, and they carried out extensive research on these paintings. They have series of paintings where they've done these kind of analysis, and this is infrared reflectogram. Infrared has ability to penetrate inside the paint layer, and therefore what you see in this first layer here is the under drawings, which is normally not visible here because the paint is over the drawings. But in infrared reflectogram, you can see all these preparatory drawings that artist did before executing the paint. Now you can see that his idea of this little finger here was initially different, and then he painted it differently. So these are the alterations. Look at the length of this finger here. This is a very rough sketching. It only gives an idea to where the fingers are going to be, and then the final modifications are almost imperative in most oil paintings of this kind, that artist changes his or her mind at the very last minute. And these are the changes that you can see. Now, this is the study about the technique of the painting, that how artists created this painting. But this is also a very important fingerprint. Tomorrow, if somebody copies these paintings, and if I have this reflectogram, I can quickly do another reflectogram of the fake painting and say that, no, this one is fake. You can see here in this painting that artist had painted this left foot here initially, because the carpet was already painted here. But then he changed his idea, shifted the left leg to a little right over the carpet, and then painted again. So if you remove the foot here, you will see the carpet is painted underneath, now hidden. So this is a very good information about the technique of a painting, that how it was created. And it also forms a very important fingerprint. This is an investigation about the cross-section of this painting sample taken somewhere from here. And you can see that this is the ground layer. Then this is a priming layer of blue color, very unusual for artists to have blue priming. And this artist has used blue priming and then the red paint over it. So all these makes, gives you informed information, decision about what the painting is, what the technique of the painting is, what the style of an artist is. If I show you another example, this is one of the very recent studies. This is the painting by a very famous Dutch artist, Jonathan Vermeer. And this painting is in one of the Dutch museums at the moment. And the technique was studied extensively. A little bit of information I have pointed here because it was not possible to bring all information. And this is again an infrared reflectogram here, trying to show you that how he created these shadows in the headwear. These shadows were created by painting a dark underlayer. So the blue is at the top, but in these areas, there is a dark underlayer, which gives this shadow effect to the painting. You can see that here, which is painted a little up here, in the initial paintings, it was much lower. It was much lower. And therefore, the artist decided to change and make it a little smaller and lift a little. Right? So all these kind of things can be studied using science. This is a very interesting work of art. This is a portrait of Alexander Mornar, again in National Gallery, London. It's in National Gallery, not National Portrait Gallery. And this was the painting, how it came to National Gallery. And it was attributed to a time of 15th century, mid 15th century to about end of 15th century. Between 1464 and 88, this was his lifespan. So people thought that painting must have been made during that period. Now, when it came to National Gallery, scientists believed that it's the painting style and the background is very unusual of a 15th century painting. They started investigating and they noticed that this blue pigment is overpainted. And how they found out? They found out that this blue pigment is overpainted, and they started cleaning it. Then they started removing it. And after removal, this is what they noticed. That somebody, after this painting was painted, sometime later, somebody decided to restore the painting and make the hat shorter. The headgear is shorter in this painting, but the original headgear of that time period was this, and the original background was this ochre, brownish ochre color. Now, how they decided to remove this? I mean, if this was original and this was the style, after removing, they couldn't have brought back. So they decided to study, and they took a very tiny little sample and did a cross-section study, and this was the cross-section. So in the cross-section, what you see, this is the ground layer. The paintings are layered structure. So if you look at a painting structure, there'll be canvas or the wooden panel on over it. You will see a ground layer, which is usually a carbonate layer to act as a filler. Then you will see a priming layer, which is in this case is the red priming layer. And then you see an amorphous dark layer, which is varnish layer. So when you see this reddish layer and a varnish layer, and then on top you see a blue layer. When you see a varnish layer, that means the painting was finished there. Varnish is always the topmost layer in a painting. And once the painting is varnished, the painting process is considered finished. Now, when you see a varnish interact between two pigment layers, that indicates that the top pigment is added after the painting was finished, after it was completed. Now, what was this pigment? They did an EDS analysis on this pigment, and they found it to be Prussian blue. Prussian blue is a synthetic pigment that was discovered in 1704 or 1710, something in between. And it was not in wide use until 1720. So this was very unlikely that this pigment was available in 15th century, 200 years ago, roughly 150 years ago, for artists to paint. So this was certainly a later addition. Now, if you look at this painting, this color that you see in the background is visible here. It's the same color. And therefore, that was the original color. Artists, the conservators then cleaned the entire painting and brought it to this level. This is what in the display in the National Gallery, London nowadays. There was similar study here in India, in Indian National Trust for Art and Cultural Heritage, that was done in 1998. And this is a very famous painting by Amrita Shergill. And if you look at the girl here, this is an infrared reflectogram here. Infrared, because as I said, infrared has ability to penetrate deep inside the paint layer. And attenuation by, the heavier pigments underneath, it can give you a sketch of what is underneath. And if you see this painting, the infrared reflectogram showed that the artist had made changes in this painting. The portrait of this girl was, this is the painting now, this is the painting at that time. So he initially painted the face slightly facing towards the front, but then he changed it, the artist changed the idea of painting the portrait as it is in the painting now. So we could see that the artist made changes to original concept of what was thought initially and painted something else. Again, role of science in understanding what could be done to artwork. This is a very classic example of trying to understand attribution and authenticity. And these are two paintings. One is original, the other one is fake. And I'm fairly sure that none of you could figure out which one is original, which one is fake. And if I ask this question to all of you, probably all of you would say that this is fake and this is original, but it is on the contrary. This is original and this one is fake. Now, this painting belongs to Carnegie Museum in Pittsburgh, but this painting is in National Gallery, London. This was acquired in 1924. In 1954, in fact, there was a scientific study done based on the knowledge that was available at that time. And the scientist had flagged that this painting might be a fake. But then a more recent study in 1998 said that no, this is this pigment is a natural ultramarine, and therefore this is a painting of the original artist, Francesco Francia, and it is heavily restored, and therefore you see modern pigments of 19th century. Again, in 2008, 2009, this painting was investigated, and it was indeed found to be a fake painting. Now, how it was found to be a fake painting, there was a series of investigations done, series of analysis done. I would show you a few of them. This is the hand of Mary here. Now, if you see here, you don't see any crack with your naked eye. The crack layer is there, very fine cracks which are not visible to naked eye. And when it was investigated, through scientific means, it was found that these are not cracks. They're in fact painted. So this is an imitation of crack which was painted on the hand to give it a look of an original painting. Pigments were collected, cross-section studies were done, scientific analysis were carried out, and it was found that this yellow pigment, which is as a priming layer below the paint layer, is lead tin antimony yellow. Lead tin antimony yellow was invented in 18th century. It is a synthetic pigment, and there was no way this pigment could have been available in 15th century. Again, the yellow pigment that you see here, and if I show you in the original this was the area I'm talking about. This is a kind of embroidery that was painted on the dress, and if you see, these were again analyzed to be lead tin antimony yellow, which was again not of that period, and therefore it was concluded that this painting is a fake painting. So attribution is also very, very, very important. Now, looking at conservation science, there are a number of ways we do conservation, use science in conservation. For every artwork or the object that we deal with, we do comprehensive condition assessment and documentation. We use a number of scientific techniques to do that. We do diagnosis of deterioration. In fact, my own research has been looking at the diagnosis of deterioration of stone. I have a couple of slides there to show you. Conservation techniques. There are a number of conservation techniques these days are being developed today to make sure that the the result that we would otherwise get from manual conservation is better using the technical instrumentation. So number of researchers in that area as well. The material development, new researches, new materials are being developed, and nowadays there is a boom of nanomaterials being invented specifically for uses in cultural heritage. Because in conservation of cultural heritage, for a very long time, we've been using materials that were developed not specifically for conservation. So they were developed for other professions, other fields, but we found it suitable to be used in conservation to the best of our ability to understand its suitability, and therefore they were being used. But nowadays, since there is quite a lot of understanding about cultural heritage conservation across the globe, people are trying to develop materials which are conservation specific. We call it conservation grade material. Therefore, reducing the possibility of any material change afterward and creating problem for the artwork. Although we cannot say for sure that the new materials that are being developed for conservation are 100% safe unless we see how it behaves. But still, there are ideas, there are thoughts being given to creating materials that would cater to conservation professionals. So when we talk about documentation and condition assessment in conservation, you see this one, we use a range of techniques, and that ranges from simple photography to advanced scientific techniques. Now, if you see this image, this is a normal light image of a painting. This is the same painting here. How do you see these cracks and cupping of the paint layer? Just by tilting your angle of the light. And this we call raking light photograph. If you change the light angle, if your object is like this, light is less than 40-45 degree angle, and then you photograph it from the top, light can give you all these undulations on the surface, which is otherwise not visible to naked eye. So slightest change in the surface topographical behavior, topographic properties of the object, you can notice with the simple photographic techniques. But we use a number of other techniques as well. And you have seen multispectral imaging and infrared imaging. All those things we use in condition assessment. I'm not repeating them because we already discussed those with technical art history. This is a very famous painting of Pietro Vermigli. Pietro Vermigli was a professor of divinity in Oxford University. So, and this was his painting, again in the collection of National Portrait Gallery, and it was studied using UV illumination. So under UV light, you see these dark areas and then you see light areas. The dark areas signify that these were the area where painting has been retouched. You don't see in the original painting anywhere because it is a meticulous job of color matching. So you don't see those retouched areas, but moment you put UV radiation on it, what happens? The original paint, okay, the paint, oil paint, basically why we call it oil paint, because the medium, the adhesive in it is a drying oil, linseed oil. And linseed oil has a property that over a period of time, it polymerizes, becomes solid, and that therefore acts as an adhesive for the binder for the pigment. Now, once it has polymerized, it gives you fluorescence in UV radiation. And it takes years for the paint to polymerize. So these are particularly newer editions of paint, and therefore it is not giving any fluorescence. And all these areas that you see dark means that painting has been heavily retouched. So the moment we get an art object, a painting or something, and if we have to study whether it has retouching, it has been conserved in the past or not, take it to dark room, use UV radiation, and you will see it. The drawback is that if the retouching is also a few hundred years old, then you won't see it, because then the paint, the oil is again polymerized and it will fluoresce. Now, this is another technique, we call it RTI. It's not the RTI which people use nowadays in India. It is reflectance transformation imaging. And this was my work when I was doing my postdoc. And if you see, this is a wall painting fragment, a historic wall painting fragment collected in and then kept in the collection of Courtauld Institute of Art in London. And this is a normal light photograph. And with RTI, you can exaggerate these paintings. In fact, I have these RTI with me. And if you allow me for a moment, I will close this presentation and I will show you that what you can see in that. Hold on for a minute. Now, can you see my screen?
Yes, yes, you can see.
Okay, so this is the fragment I was talking about. And if I show you, this is the normal light photograph of the painting. Now, what is RTI? RTI is basically a collection of series of photographs. And the software was initially developed by Hewlett-Packard, and it was called polynomial texture mapping. They developed this while trying to develop video games. But this is used in cultural heritage. When they call it polynomial texture mapping at that time, the technique is that you keep your camera static over the object and move your lighting direction for each photograph. And you build a series of photographs with a different lighting angle. And then you upload all those photographs into the software and it builds into a polynomial texture map. Now, what happens, in polynomial texture mapping, you needed to supply the direction and angle of light in the XYZ directions. But when the reflectance transformation imaging software was developed, all you need to do is to keep two shiny snooker balls in the focus of the camera, in the field view of camera and image. Because those shiny balls gives you the reflection, the software reads the light direction and angle from the reflection coming from those spheres and gives you that image. So once you build this RTI image, here is a trackpad. You can rotate your light direction. And if you notice it here, let me zoom it here a little bit. Zooming is a little difficult. Now, here you see a couple of scratches here in the paint layer. Now, these scratches, what they actually are, when you turn the light around, you will see it. Here it is. So this is what RTI can give you. These are dents, which are quite deep here, which is not visible in the naked eye when you have light coming from the front. So this is actually a game of light and shadow. Once you have uploaded a series of images, like in the number like 30, 40, 50 images from different angles, light coming from different angle, camera should be static, you get this image. I'll go back to my presentation. Okay, so this is what you can see. It gives you hidden information about the object and a lot of things one can do. I mean, nowadays people are trying to use different kind of radiation to do RTI, like UV RTI, IR RTI, and things like that. The second aspect of conservation science is understanding the deterioration problem. And deterioration can happen to any material. It can happen differently in every condition. The same material can behave differently. Now, this is a painting from Nagaur Fort in Rajasthan. And you can see that the faces here, these are wall paintings, faces here and the body parts have turned black. Now, it is very well known that lead white turns black. And there are different mechanisms how it turns black. Initially, we had believed that lead white turns black because it reacts with the hydrogen sulfide or sulfurous gases present in the atmosphere, converts into lead sulfide. And that is black in color. And it does happen. But a recent study, although not on these paintings, but a recent study has also shown that the lead white can convert into lead dioxide, which is also black. So this was a lab-generated study that was conducted, and you can see that this is a diffraction pattern, and you can see that all these P, I've forgotten to add the information about it, but these are all indicating that the formation of lead dioxide is another possibility of how these pigments convert into black. This is part of my study. I'm sure you must have seen these kind of images across the country. If you go to a historic building, you will see that parts of it contains whitish salt efflorescence at the surface. This is the image of Qutub Minar. And if you go to Alai Darwaza at the backside, you will see these kind of images. And these are all salt damage. Salt damage, where all the salts come in from. Obviously, from the ground, capillary rise. So capillary rise takes place, salts, when the water rises in this porous material, all the salts dissolved in water come in. From the surface, water evaporates, leaves the salt behind, and the force of growing crystal within the pores can generate enough stress over a period of time to push the surface layers apart. And therefore, you can see that this decoration continued here as well, but it is gone here. This decorative piece continued all the way here, but it is gone completely. The surface details are gone. You can see salty white is efflorescence here. If you go in summer, you will see all these areas white, completely white. And I'm sure you must have noticed in other historic buildings as well. You will notice more in concrete building because concrete is very compact structure, very fine capillaries. So higher capillary rise. So this traditionally has been accepted that it has been noted that most of the chlorides and nitrate that are seen in the upper layers of efflorescence, people don't see sulfates, and all the time you see either sodium chloride, sodium nitrate, or potassium chloride, potassium nitrate coming at the surface. Now, groundwater doesn't have only sodium chloride and potassium chloride and their nitrates. They have all kinds of salts. They have gypsum, they have sulfates, they have sodium sulfate, they have calcium sulfate. Why do those salts do not come to the surface? And that has been studied in Europe for more than 30, 40 years, and people propose different models. One model said that all these salts have different solubilities, and depending on their solubilities, the salts crystallize at different locations. So if a solution is climbing up in the capillary, and the evaporation is constantly taking place, once a particular salt reaches its saturation level, it crystallizes out, and the others continue moving, and therefore you only see the lighter salts like sodium chloride, sodium nitrate out here. But this is not the case. The second model suggested that the different salts have different properties. Their viscosity, surface tension, vapor pressure are all different, and therefore they crystallize differently. But these models can be held valid only when these salts are acting individually. When you have situation like groundwater, all the salts in the same solution. Now, viscosity, surface tension, vapor pressure will be same for everything. It can't be, it can't act differently for the same solution. And therefore, there has to be something else that leads to these fractionated crystallization of salts. And we started looking at it from point of view that the stone is a chemically very active substance. And it is not possible that most of these salts, when they dissociate into their ionic counterparts in the water, can move freely without interacting with the constituents of the stone. And what we noticed that this is basically the entire stone is acting like a chromatographic column. They retain salts according to their preferential retention capacities and leave salts when they, so if you look at this diagram here, this is calcium, this is magnesium, this is potassium, and this is sodium. So sodium, so what we did, we used 1 millimolar concentration of salt. We flew through the stone sample, and we noticed that sodium is the first one to achieve equilibrium, which means the stone as a system throws out sodium salts faster. And that is why you see sodium salts on the surface. So with potassium, because of their higher ionic exchange capacities, calcium, magnesium, or other divalent ions or trivalent ions will remain inside the porous matrix. So what are the implications of this study? We also, before we go on to implications, so this was the flushing we did. So at the end of it, we found that the stone sample which we are testing is equilibrated with 1 millimole of all these 4 ions. Now, we used a replacement technique. We flushed the same core with strontium nitrate, strontium being trivalent, replaced everything. But even the replacement was in the same order. If you see, sodium was replaced faster, potassium was replaced second, and both divalent ions of sodium and magnesium and calcium were last to be eluted. So this suggests that stone is acting like a chromatographic column, and it retains ions preferentially with the ion exchange sites when the salt transport takes place. And that is precisely the reason why we only see sodium chloride and sodium nitrate, or potassium chloride and potassium nitrate at the surface. We also did a frequency geochemical model to see whether our results can be validated. And have a look. The solid line is a frequency model. The dotted lines are our experimental result. What an excellent fit. So it suggested, the entire study suggested that stone is acting like a chromatographic column. It is retaining certain ions, certain salts preferentially within its core, and is eluting some outside to go and crystallize on the surface. So what are the implications? If this happens, these salts like sodium chloride and potassium chloride, these salts exist in only one phase. The damage caused by these salts are much lower as compared to salts that can stay in multiple phases, like sodium sulfate, for example, in two different phases, like thenardite and mirabilite. One is anhydrous sodium sulfate, other one is with 10 water of crystallization. Now, and both of these have different RH equilibrium conditions. And when the RH fluctuations happen, it will crystallize, transform from one phase to the other, and other to the previous one. And therefore, these would lead much more damage to cultural heritage, because the transformation is happening multiple times. Something which is eluted at the surface, crystallized at the surface, would not be that dangerous as compared to something that is retained inside. So the salts that are retained inside the matrix of the stone are much more dangerous in terms of their ability to deteriorate the stone. So this was the study. We went further to look at what happens when the environmental transformations happen on a very short scale. And environmental fluctuations happen. Like, suppose that this is bright sunny day today. Suddenly rain comes for half an hour and then goes back. Temperature back. Sun is back. Temperature is back. Now, so we artificially created these kind of scenario, and this is the time-lapse video imaging which we did in Nagaur Fort, where these are actual on wall painting surface. Since it is a microscopic image, you don't see the painting behind. And these were the environmental conditions that were maintained. So we locally maintained these environmental conditions. You see it about 90%, just above 90% moisture, and about 25 degrees Celsius temperature. And the salt was analyzed as potassium nitrate, which has equilibrium moisture content of 90%, which means at 25 degrees Celsius, if you increase the humidity above 90%, it will dissolve. And if you reduce it, it will crystallize. Now, what you see in this time-lapse video imaging, that in this humidity, the salt is dissolving. The salt is dissolving. But while it is dissolving, you see newer crystals being formed here. There is dissolution on one hand, but the crystallization on the other. So this indicates that smaller fluctuations on a shorter time scale would lead to massive catastrophic damage, because whatever moisture is gained by the salt will lead it to dissolve and recrystallize, form different crystals. So crystal habits, once they were crystallized, they did damage, they dissolved and recrystallize, the damage would happen again. So the damage in case of cultural heritage by salts depends on how often they change their phases. And therefore, this kind of scenario where the change is happening on a very short time scale can lead to catastrophic crystallization and massive damage to cultural heritage. So this is something about diagnosis of deterioration, trying to understand how deterioration happens. In terms of conservation techniques, we use a number of techniques. Now, this is a typical graph that is shown how we monitor climatic conditions in historic buildings and in museums. It is internationally recommended that the humidity in the museum should be around 45 to 55%, and the temperature between, say, 22 to 25 degrees Celsius. This is a very narrow range. And for museums, particularly in a country like India, it is extremely difficult to maintain such a precise climatic conditions throughout the day and in the night. You need a very dynamic system to control that. Air conditioners don't work that efficiently. So this monitoring happens all the time. And since there is a very narrow bracket between 45 to 55%, it is often very cumbersome to maintain that and very expensive too. You need HVAC system to maintain such a environmental condition. So nowadays, people are researching on actually trying to find out. I mean, these are guidelines. 45% to 55% are just guidelines that these might be an ideal situation. But whether we need to actually maintain that humidity and temperature, we need to know from research that what material can be fine at what temperature and humidity. So if you look at some of these researches which are happening, people are trying to find whether materials can survive at a broader range of humidity. And here you see this research has suggested that between 32 to 62%, the yield point is very marginal. And therefore, you can have environmental control on a larger scale. But when you have 100 different types of objects in the museum, you need to have research on each of those materials to be able to find out at what level they are comfortable. So a whole lot of science required there as well. In terms of conservation techniques, nowadays, laser cleaning has become very, very, useful. Now, this is a painting which was damaged in fire. Damaged in the sense it was not burnt, but the soot and everything deposited, making it opaque. And this was, so people tried cleaning with normal solvents, the way we used to do in conservation. We still do, using normal solvent cleaning. It wasn't possible. Most of the solvents were either not useful, some which could clean the surface deposition could also damage the internal paint layer. And therefore, it was decided to use a UV laser, a controlled UV laser, to clean this painting. And you see beautiful result. This is the area that is cleaned. These are still dirty. This is the patch that is showing. Again, here you see this is a wall painting. This area is cleaned, and this is still under a coat of grime, which is still on the painted surface. And this is cleaned by using laser technology. So these are newer developments in science that are happening, applied to and are being applied to cultural heritage. If you look at Research and development. A lot of research is happening today in order to understand, as I said, what materials could be suitable for conservation. And this is development of gel system to clean paintings. I mean, using solvent is an age-old technique to clean historic works of art. But solvents, most of them are organic solvents, most of them dangerous for the human health, and therefore people across the globe are trying to do away with those dangerous solvents and trying to develop cleaner ways, safer ways of cleaning artwork. And these are genesis of gel system. You can see there is a gel piece of a rigid gel placed on the painting. It's being lifted. This is painting in a normal light. This is in a UV radiation, showing darkened varnish as white fluorescence. Again, this is in normal light, and you see wherever the gel was placed, you can see the underneath area was completely cleaned. And this is again in UV fluorescence. Again, in UV fluorescence and in normal light, you can see that using the gel, the aged varnish was removed, and all you need to do is to prepare the gel, cut long sheets of it, place it on the object, cover it for some time, remove it. And this conservation process can be much, much faster. Otherwise, to clean with solvent, painting of this size might take weeks, if not months, right? So a lot of things. Again, this is another research trying to a gel loaded with a micellar solution. A lot of research is being done in developing micellar solutions and microemulsions for cleaning works of art these days. And the research is full of, particularly Western world, is full of developing all these materials to effectively clean artworks. And you see, this is, the weave of the canvas that were being cleaned. And you can clearly see that before cleaning, this has a coat over it, is a synthetic coating over it. And after cleaning, the fibers are completely cleaned. Although you still see in the residues here and there, but it is completely, most of the area is completely clean if you see it like this. So these are newer ways of developing materials to clean and conserve artwork. There are a lot of material investigations that are happening into trying to find nanomaterials for cleaning and consolidating works of art, which can be better than what materials we've been using for now. And here is again a cleaning system. This painting had an acrylic coating on the top, and this was cleaned using gels in this by creating a dispersion of oil in water microemulsion placed with a gel, and this how beautifully it is cleaned. In terms of developing new materials, I'm sure most of you would have encountered problems of breaking glass in your own houses. And then if you try and join it, you will see the joints no matter what you do. These days, if you see, this is a glass lamp. A corner is broken here, and these are two pieces which are broken and joined with another adhesive. You can see the joints here. These were cleaned, removed, 3 different pieces. There is a tiny little piece here, and then joined again with a conservation grade materials, and you won't notice where the joint is. Why this happens? Because these days, the materials which are being developed, particularly for conserving glass, are kept in mind that the refractive index of the adhesive should be closer to that of the glass. If the refractive index of the newer adhesive is closer to that of the glass, you won't notice the difference between these. Most difference you would notice when there is air in between, because the refractive index of air and glass are way apart. So if you have an adhesive that matches the refractive index of your glass, after joining, you won't see the joint. You will see it only with very careful examination. Otherwise, it will look like this. So these are newer research, newer developments that are happening. So I come to the end of my presentation. There is endless scope for application of scientific techniques in the study, interpretation, and conservation of art and cultural heritage here in India. It is a very well-developed discipline in the Western world, but in India, it is still are taking a baby step. So there are ample opportunities to create cross-disciplinary collaborations, try and bring institutions like IIT to collaborate and do research in cultural heritage. And who knows, maybe decades later, we would be in the same condition where some of the Western countries are. So this is end of my presentation. This is my email address. If anybody wants to write to me about, with any question or anything that you want to discuss. And with this, I would close my presentation. I think I've taken away a lot of time, about an hour and 15 minutes. So, Shamik, over to you.
Yeah, so that was some amazing talk actually. Thank you for the insightful and stimulating talk and sharing your work, as well as so many different examples from different parts of the world, and it's it sometimes you took us to that particular era, while you're seeing the paintings and you're analyzing the stuff. So yeah, so the floor is now open to questions.
Yes.
So any questions, you can just, the audience, I request the audience to type their questions. Also, like, if you want to speak, you can just raise your hand for it. You can directly speak. So yeah, so so we can give a few minutes to the audience. So I had a few questions.
Yes. By all means.
So you said that we are studying the deterioration of the various materials in various artifacts or objects, like paintings and all. So the environment is very important, as you just said.
Yes.
For example, does the overall climate affect it? For example, outside paintings or frescoes will degrade more in tropical climate, such as in India, or will it degrade less in temperate or colder climates or something like that, or in Europe?
Yes, it does happen. I mean, the kind of temperature and humidity fluctuations we have here in India is enormous. Like, you can see that in monsoon season, you have humidity going up to about 90%, whereas in the summer, particularly in Delhi, humidity comes down to about 30-40%. Now, this is a huge fluctuation that happens. In most temperate climates, humidity fluctuations are not that high. And therefore, the similar kind of work will survive better in those climates as compared to this climate. With the warm and humid climate here in India or the Indian subcontinent, you would also have lots of microbiological growth that would come up if the sites are abandoned or unused or unkept for a long time. So, which doesn't happen in most of the Western countries where climate is temperate, because most of these biological growths need high humidity and high temperature to survive. So yes, environment plays a very important role in how the artworks will survive. In museums, particularly in Western world, they have different challenges. Since they have temperatures coming down to say -10, -15, many of those European and American part of the world, Canadian part of the world, they have challenged to bring it to 18-20 degrees Celsius. So they have to spend more to bring a colder climate to, climate which is conducive for artwork in museum. Whereas in India, barring a couple of weeks in winter and maybe a couple of months in summer, the conditions, temperature and humidity is more like stable for Indian museums.
Okay.
But still, we do not have enough resources to manage climatic conditions as we want, because once it rains inside, humidity increases, and there is less awareness as well. I mean, I've seen series of museums in remote areas and smaller towns, and they would use empty household air conditioner thinking that it will do the job. it is worst, in fact. I mean, objects are fine without air conditioners.
Okay. So that means like in one slide you showed that the salt formed solutions, they crystallize and then, dissolves and recrystallize. So that actually damages your structure, right?
Yes, it does.
The
Yes.
material.
Yeah.
So does the same thing happen when you have those, freezing and thawing of the water itself in
Yes,
S1?
exactly. It is the same. I mean, freezing and thawing also does the same kind of damage, because salt crystallization, what happens? Salt crystallizing because water is not available to keep it in solution form. In freezing as well, the same thing happens, because when the water freezes into ice, there is less water available to keep salts in a solution form. And therefore, when you reduce the temperature, then again salt crystallizes.
Okay.
And the similar kind of damage.
Okay. Okay. And also, like one interesting thing I noticed was when you were showing the, cross section images of the cross section of the
Yeah.
painting,
Uh-huh.
and it had kind of like paints from different eras, right? Like almost like
Yes.
500 years here and there.
I'll go back to this again.
Yeah. So, do you have the option, like you, of course, like used infrared imaging and all? Uh, do you have the option of using, radiocarbon dating or something on each layer, or how much sample do you need for those?
Radiocarbon dating, radiocarbon dating is not that easy as we understand. You're talking about this image, isn't it?
Yeah, yeah, yeah.
Here, for example, radiocarbon dating can be used in this varnish layer, right? In terms of radiocarbon dating is not an absolute method of dating. It requires comparison with the carbon 12 and carbon 13. So, in case of materials like this, although it is possible to do carbon dating, but here in this painting, there is not enough material to do radiocarbon dating. For radiocarbon AMS dating, uh, which requires minutest quantity of sample, but it still requires about 100 milligram of sample.
Okay.
It is not possible to extract 100 milligram of varnish from a painting like this. This layer would be like, couple of micron thick. So you can't have 100 milligram of sample available for radiocarbon dating. So radiocarbon dating doesn't work that way.
Okay.
And certainly you can't do it on pigment, because even if pigment contains carbon, it is inorganic carbon. You won't be able to find radiocarbon in that.
Okay. But I think this was a nice example, like how they change.
Soumik, can I ask a question?
Yeah, 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 Professor Ram.
Yeah, Satish, very interesting talk. Now,
Thank you.
I would like to know, how much in our country we work in terms of, creating a database, especially in terms of the different monuments, because the materials of a different kind. See, I had an experience going to the Humayun's tomb when they were restoring it in the last 10, 15 years. They have done a very good job. I mean, since I have been there several times.
Right.
Over there, I think the involvement is from an outsider. I mean, probably they had the finance, but many government places, if it is not ASI, and then it becomes a problem, right?
Yes. I mean, forget about database of material. We do not have a complete database of all the monuments in the country.
Okay. No, because I was thinking, in the north itself, if you look at it, there cannot be much variations with respect to like Rajasthan.
Exactly.
Various buildings.
We only have the database of monuments which are protected under government. Even the monuments which are protected under the state governments, because then there is Central Archaeological Survey of India, which has control over certain monuments. And then there are certain monuments in each state where state governments have their custody. So Archaeological Survey of India, I'm sure they have a database of all the monuments which are there under them. But state governments, many of them would not have a database of how many monuments they are preserving. So in terms of developing material database, I mean, this is an ideal situation where, we need to start doing research to figure out not only, I mean, if you go to any monument, you will find 10 different types of stone, you will find 10 different types of plaster, pigment, and all these kind of things. Now, in terms of museums, the quantity is even bigger. You have 1,000 different types of objects with different types of material, and creating a database of each kind. I mean, in the Western world, how they're able to do a scientific study and attribute, oh, this painting belongs to Jonathan Vermeer or this painting belongs to Pablo Picasso. Because they have built an extensive database of their materials and their styles to be able to figure out, okay, this painting, we don't know who has painted it, but we find these kind of materials, we find these kind of techniques used, and this looks very close to this X artist or Y artist, and therefore this may belong to that artist. Although many times it is not possible to correctly attribute, but in majority of cases they do attribute because they have built a database.
No, but what is the problem? Why we are not able to do it? I mean,
we have no unified research. I mean, in Western world, if you see, research are not duplicated. People collaborate. The biggest problem we have in our country is that we don't collaborate. If I think that I alone would be able to document, or somebody alone or one organization can document all these things or prepare a database of everything, this is enormous task. It can never complete. So we need multiple players to join hands together to try and document, to try and build kind of a database of every different types of material, maybe stone, maybe plaster, maybe pigments, even metal artifacts, for example, paintings. Indian paintings, I mean, look at the variety of painting. Every state has 3-4 different types of painting native to them. Where is the database? We don't know.
no, because I think we probably discussed with this issue. Even Taj Mahal, I'm sure that they would have tried different times at different places.
Yes.
Right? I don't think that they would have come overnight, one particular place and then that finally. So,
if
there will be definitely, even in Agra, I think I visited 2 places where they call it as a Chota Taj Mahal or something else.
Yes.
And so they would have done some, preliminary studies, some kind of a prototypes here and there. And if those materials are available and if there is some study, then it is possible to, construct a better picture about what happens. So no such things are available.
Nothing as of now. There is no scientific study published on Taj Mahal that, whether the entire marble that is used in the Taj Mahal is from the same quarry or they have used marble from different quarries. And I'm pretty sure that it is not possible for anyone to have so much of marble from the same quarry. There might be marble coming from different quarries where, maybe main mausoleum was built from marble, the best quality of marble coming from one quarry. But then the side walkways and everything else must have built from a marble coming from elsewhere or locally sourced. We don't know as of now because there is no study. Agra, from Taj Mahal, if you travel 2 kilometers, you will find Itmaduddaulla's tomb.
I've been there, yeah.
Itmaduddaulla's tomb have the entire decoration is fossiliceous stone. So if you look at it closely, you will see the marine insects buried in the stone, which is fossilized now.
I see.
There is no study of that, where this has come from. We don't know which quarry. I mean, I have some idea that, in Rajasthan somewhere there was a quarry where fossiliceous stones were found. But there's no research. There's no research to find out which quarry it was taken from. There was a quarry somewhere in Pakistan, Sindh region as well, where there was fossiliceous stone. But there is hardly any systematic study in looking at those stones, their properties, their characteristics, how they are sustaining in this environment. Agra is one of the most polluted environments. How they are sustaining, what kind of changes are happening. There is nothing of that sort.
Because the degradation also of the different marbles will be different, right?
Absolutely.
So at
Absolutely.
that time, I doubt
Depending
that
on
they
their
would have been
composition.
aware of all these things.
Yeah, a variety of marbles. Normally, the marble that we use in our houses, if you see, some of those marbles will have a streak in between somewhere.
Correct.
Now, it is not that the marble was born with that streak. Marble has chemical composition which, when exposed to environmental conditions, some minerals alter their composition. Some mineral will change their color. And that is how you see all those streaks. And you see those things in Agra's Taj Mahal as well. The black stone which we are talking and trying to investigate, is turning gray. We don't know why it is turning gray. This is one good research project that we can investigate why the black stone is turning gray. What is the composition of black stone? Where it was sourced? What was the quarry? Whether it is a result of atmospheric pollution or any conservation intervention that has been done in the past, or it is a natural alteration of the stone minerals itself.
But is it known that, what is the kind of compositional variations? Because there are 2, 3 different minerals are there part of the, apart from calcite. Now, is it there, different parts of the marbles, whichever the different quarries in Rajasthan itself? Is there any data, any study on how the composition vary, or nobody?
Not that I've come across. I mean, if Geological Survey of India has done any of these kind of study, I mean, I'm sure that they would have not done anything on related to Taj Mahal or any of the monuments, but they may have some data about variations in natural stone from one quarry to other. But I have not come across any such data.
Okay, so even the geologists probably have no interest, or probably, there is lack of funds. I don't know.
I mean, that is the reason why we need to have all these organizations pool in together and try and take different things that can be done at organizational level. And that is where the roles of IITs and other such institutions come into play, that, if the IITs and other such organizations start creating centers and doing research in cultural heritage, then one day there'll be sizable amount of data generated and then built into a database.
Saumik, there are others who are asking questions, I think. Rajesh, probably, I don't know.
I don't see any remark in the chat box for now. Okay, so if probably they can contact you directly if they have more questions later.
Yes.
Okay, I think it's already past the time, so we might have left. But anyway, so I think thanks again. Thanks a lot for
Thank you.
this very nice talk. Actually, this is one of our most unique talks so far in our platform. So
I
thank
mean,
you
it's
very
very
much.
generic. Maybe next time we'll do something more specific to look at the problems where we share more data and more technical information about one particular issue or
Sure,
something
sure.
like that.
Yeah, sure.
Yes.
So when when all this is over, like we would like
Yeah.
you to come over physically and then give another
Physical talks have different charm.
yeah, yeah. So that would be very nice. And thanks again for agreeing to come to our platform and give a webinar on this.
Thank you so much for having me.
Yeah, and also I'd like to thank Professor Anil Elias, who is our HOD, and also Professor Ram Ramaswamy, and also Professor Ramanan for making this happen and for their constant encouragement to keep this webinar series going on. And I would also like to thank Professor Janakiram and Professor Vishwarup, who are co-organizing this webinar series along with me. And on behalf of our department, we would like to wish you all very good health and in these difficult times. So please take necessary precautions and stay safe. And we all hope to see you again soon in the next talk. Okay, so thank you everyone for attending today. And thank you, Dr. Pandey, once again. And
Thank you.
have a good
Thank you so much.
Thank you.
Thanks a lot.
Thanks, Satish.
Thank you.